Hi there! In this video I am going to go and attempt to solve day 16. I am a bit careful with my words because today I've seen that in the leaderboard here for day 16 it took like 1 hour and 4 minutes for the 100 fastest people to solve this. And so that's quite a lot of time. Hopefully the video is going to be shorter. So I'm planning to at least solve part 1 and yeah, we'll see. Maybe I try part 2, but I can't be sure that I will solve it. So in this problem we have this dataset and we're just going to start by parsing it. That's what we do every day. So we push that into our local text file. We use our template here. I should comment that in the template. Okay, so here we read the file, we split on the lines, and here we return lines.map. I need to actually do that as well in the template, because that's what I'm doing every day. I'm mapping here. Okay, so what do? We have this kind of data, and you know that when we have such a sentence, I love to create a regular expression. So const regexp, and here we have a first pattern, which is here we're gonna call that q valve. And here this is AZ several times. I don't know if this is always 2 times. Let's do that. Just 2 letters. Here this is the flow rate. Can it be negative, the flow rate? I hope not, otherwise that might make things even more complex. Flow rate is always positive between 0 and several digits. Okay, so here we have here flow, this is several digits, and here we have to write yeah, actually here we can just say something like other valves, and here we just take the full rest of the string. Here this is the beginning of the string, here this is the end of it. Let's try to see. Const match equal regexp dot match. Oh no, it's the opposite. It's line dot match regexp, and here we console log the match. It's always good to do things slowly so that we make sure we solve the problem correctly. So parsing is going to be the first thing. Here we always need to just take the groups. Because we used this syntax, we actually gave a name to these capturing groups. This is a syntax to give a name to a capturing group in a regular expression. Oh, cannot. Let's console log the line. Before we do that, let's see, is there something where it valve HH has flow rate 22, tunnel leads to valve GG. Valve, oh, there can be S or no S here. That's sneaky. What's up? That's flow rate, tunnel, oh, tunnel. So sneaky, there is a S that can appear here. Tunnel leads, oh my god, English language, you know. S or no S. Okay, we parsed this correctly, which is, it was funny actually to do this parsing. It feels a bit like they are being funny with us. Now we need to split the other valves. So here we could just return, yeah, let's return here instead of match we have valve, flow, and other valves. I don't know how to write that. So it's valve, flow, and flow is we need to parse int the flow, otherwise we have a string and we know we need to get rid of we need to convert all the numbers into all the string that contain numbers into actual strings, otherwise that's a mess. And here for other valves we need to split with a comma space. Whoops. Now we can console log the input. Let's see. Yeah, we have our flow, we have other valves. So the first thing that we know is that we will never open a valve that has a flow 0, because we have a specific amount of time that we need to respect, which is 30 minutes. Constant time is equal to 30 minutes. And because of that, we don't want to spend 1 minute to open a valve of flow 0, because it will not change the final value, which is flow times the okay, so basically here we have a graph. And we are going to need to move through the graph. So what kind of tools do we have in our toolbox? We have pathfinding, like Dijkstra that we've made, we wrote already on one of the previous days. However, here there could be a loop. For example, you could say, okay, I want to go to BB to open the valve, then I go back to A, and then I go to II. Yeah, maybe that's not a thing, but yeah, maybe from A you go to D, then you go back to A and you go to B. Something like that, you know. Actually, let's look at the path. Here, the example path. D C B A H A. Okay, so here you see you go back to A. So you were in A here, and you go back to A here. So basically there can be loops in our path, which is bad news, kind of bad news, because it means there are going to be a lot more option, option in our, like in the pool of possible path. It's going to be enormous. So we're going to be focusing on solving part 1 because we want to have some results, and it will definitely not be the right solution for part 2. So I think basically, because we have these loops, we can do BFS or DFS, and yeah, I think I would love to do BFS, because DFS is really not really the right option for optimization. So I'm going to pause, open the pseudocode, and we're going to write that. Okay, so this is what we need. We need a breadth first search. And yep, the idea is that maybe we find a way to cut some path. And yeah, because we are, see for example here, like on this maze, they reached the end, and so there are some cells that they didn't search. So yeah, see here, there are some cells that they didn't search. So that's kind of what I would like to do in our case, like prevent some cells from being searched. So yeah, we're just gonna take the full thing here and we're gonna paste that inside our editor. on the right here. Oh, it didn't work. Okay. The idea is that we should follow that to implement our DFS. BFS. So we have a graph because this list of array is a graph. We could connect we need to find a way to find D and not go through the whole array every time. Is that important? Maybe it is. So we're gonna change this from an array here. Instead of being that, we're gonna create an object. So let's try to do that. So here, instead of returning that, we const array. I would like to return an object here. Return object dot from entries. No, what is it? From entries are two. From entries. Oh, we return the key. Okay. Okay. So here we do array.map x, and this is x.valve and x. And if we do that, I believe we have our object. Yes, we're good. So we have our object here. So now when we are on the point AA, we have like the options, and we can directly go there without having to go through the full array. So let's start our BFS, G and root. So there are going to be like a lot of things to store inside the state. So the state, basically we have a state that's going to contain the node. So for example, at the beginning, const root, what is the state? Node is, we start with at the place AA, if I'm not mistaken. Right? Currently at AA. Have computed, we have the flow so far that start at 0. And we have the open valves as well. Open valves. Yep, that's it. That is the state. And basically, yeah, we're gonna have to keep this in memory for each node of our tree. So that's gonna be interesting. So we need a queue. So it can be a const queue. It's an empty queue. Oh, we need to check. We need to label as explored. So here we don't need to do that because we can go back to the same node. We just cap our exploration at 30, the depth 30. But we don't need that. That's gonna be interesting. I'm not sure where I'm going, but we're going there. So here we say while queue.length is above 0. What do we do here? We take the first element of the queue, so const current is, oh, we forgot here. We have q root, so we need to do q.push root. And here current is equal q.shift. Actually, here what we need as well, we need to know the turn, the current turn. Turn, or the current time is time. That's it. We have 30 minutes when we start. So this is it. We have all of the information that we need. So as long as the queue is not empty, this is our current node. And if v is the goal, so if v is the goal, then we return. But here our goal is not, we're not gonna write that because we are like modifying the BFS a little bit. For all edge from v, okay, so now for all the adjacent nodes, so we need to create all the possible actions from this route. So one action is to open the valve. So here we need to say if current.flow is above 0, we don't want to open a valve that has a flow 0 because we're losing time. That doesn't make sense. And current.open valve of current.valve. No, current.node, sorry. So if we don't have that, so if the current flow is above 0 and the current valve is not open, then we need to open it. So we do q.push a new state that has the node is the same as the current node. So let's do node current.node time current.time -1. What else? The flow is so here for the flow we need to create a function that takes open valve, function add flow open valves, yeah, we just return the open valves and basically, oh yeah, we actually need to return the input here. What do we call that? We call that the graph. So graph and open valves. And so here we need to go through for in key in open valves. We don't need that. We const sum equals 0 and we need to say graph of key, sum plus equal graph.key.flow. Here we return the sum. So here I think it's wise to actually test that. Before we do the full algorithm, we want to make sure we are able to add the flow. So console log, for example, we add flow, we have our graph, and we say the open valves it's only AA. Maybe open valve should be a set instead of an object. Yeah, let's just say AA true, that's it. So here we display that. Oh yeah, I've put typical mistake. I've put a constant variable instead of a let. Okay, we have zeros. That's expected. Now we need to display, let's say BB. It should be 13. Now let's say BB and JJ. It's 13 plus 21, so that 33. What? Oh no, 34, sorry. Okay, so we have a function that's able to say, depending on which valve are opened, what flow do we get for this specific minute. So now we can uncomment that and go back. Here the flow is current.flow plus add flow, the graph, and current.open valves. Then here the open valves is we do current.open valves and we add current.node set to true. That's a bit of ES6 syntax, but here what we are seeing is we are duplicating the object current open values and we are adding an extra property. The key of the property is the value current node and the value of this property is set to true. That's it. So we have that. We are pushing here. So here we need to check as well. We need to check if time is equal to 0. Then const endings endings dot push current. Yeah, we're gonna do that, and here we're gonna continue. So basically, if we don't have any more time, if we reached 0, then we are pushing the state inside an array here, and we are just stopping things. Here, we have one thing. So here, this is the end condition. Here, this is opening the valve. And here we are moving to another valve. So basically we need to for off valve of graph of current.node.other valves. So basically we have our current node and we need to go through the graph to the right value here to have this list. And now we have the list DD and BB, so we just need to do q.push. The node is valve. The time is current.time -1, because when we move to another valve you spend 1 minute, and the flow is the same thing here, and open valves set to the same current.open valves. We're not touching that. Okay, so here with that, we should be exploring the full map, the full graph, and stop when we've reached 30 minutes and push all of the options inside the array ending here. So here we're just going to display ending. And I believe there will be a ton of optimization for that. Yeah, let's try that. Yeah, see, this is taking forever. So already for part 1, we have a challenge where this is taking a lot of time. What should we say? Here maybe we should display console log q.length, just to have an idea of where we stand. Okay, so basically we're just going to infinity. So let's see. Here I did current time -1, current time -1, so that's correct. And oh, what is time equals 0? That doesn't make sense. It's not time equals 0. It's current dot time equals 0. Oh my god, that's why. So I was checking, is 30 equal to 0? But no, we need to check if the time is equal to 0. That doesn't help so much. We are just pushing more nodes. So let's see. Yeah, that doesn't make sense. Basically, let's see. At worst, we have 3 new options. So it means it's 3 to the power of 30. Is that it? Oh my god. I don't know if you see this number, but this number doesn't look like something we want to be dealing with. So basically here we are exploring the whole space of options, and we are gonna need, oh no, yeah, it's even more. It's because you can also open the valve. So here, for example, from this node you have 4 options: opening the valve, doing this or this. So it's maybe something like 4 to the power of 30, like the worst. You know, of course it's lower than that, but yeah. So we need to think a bit how we can cut down on the space. Maybe we can display a bit of our here we can console log the current. That's going to be a lot of things displayed, but I think it's good to just see a bit where we are. Maybe there's a bug. Okay, so here, yeah, we have 0 flow. We're just going back and forth between those nodes without ever opening anything. Let's see. So basically now we need to find these optimizations. So no valves are open. You move to DD. You open valve DD. So what we need to prevent moving in the map and never opening any valves. That's something that's happening. So the obvious thing is to say, okay, you haven't opened any valve, it's minute 5, then up, that's it. But here, yeah, we already spent 10 minutes without opening any valves. That's a lot of states that we can remove. So we can say something like, let's try that. If current time is below time minus 10, so this is like we spent 10 minutes, and current dot flow is equal to 0, continue. So here we skip this node. That's very ugly. I don't think that's not the best option, but oh, what? Current time is below time minus 10 and current.flow is equal to 0. Then we continue. Oh yeah, what? I think I made a mistake somewhere. So here we're just gonna console log current. Time 19. Interesting. Okay, so here what I would like to see is what's happening here. After time 20. Okay, so here we, oh wait. I've made a mistake here. Current.flow. Okay, so here I was never opening any valves. Current.flow is the flow of the valve, the flow of the state. We need to check here the flow of the current node. So we need to do graph of current node dot flow. This is the flow of the valve. If the flow of the valve is more than 0 and in our current state we haven't opened this valve, then we need to add this option. So now we should see a lot more of this, a lot more open valve. And here we're just like removing these things that never opened. Oh yeah, but that's already too many states. We haven't reached even 19 yet. Here we're still at time 20. That's crazy. Yeah, I see, we like maybe let's do 5. After 5 moves, you should have opened a valve. That's here we're removing something, but still we're gonna have, and basically here this time it's going to go down slower and slower. Here we have time 20, 19, and it's going to be slower and slower because there is always more nodes, so it's growing exponentially. So we need a way to cut that. That's interesting. So here, instead of true, we can store open valve. We can store the time we had. The time here we can store current dot time minus 1. So basically, instead of storing true, we'll store the time when we open the valve. And so we can say something like, if we haven't opened a valve in like 5 minutes, object dot keys dot of current dot open valves. If we haven't opened a valve in 5 minutes, then we need to stop. I don't think this is the right move, but it's just like an ugly optimization to try to see if we can like cut down a little bit this incredible space. So here we need to say math.min, the minimum of all the time we opened a valve, and here we have time in case in case this is empty. It should be above current time, no, this -5 should be above current time. Let's see. Yeah, it's still taking forever. Yeah, we reached 19. That's interesting. So it looks like the DFS approach, BFS, is not the right one. There are far too many states. I think we need to find what moves are not correct. No valve are open, you move to DD, open valve DD. I'm gonna do a bit of offline thinking just to to progress on that. So here you can see that this is totally wrong because there are like, you have to do like a lot of moves here before going to the next valve that you open. So I think I'm gonna pause here. So I've been thinking a lot about our approach, and I think the problem is that we say, okay, let's go to valve FF. But we know valve FF is never useful because it has a flow rate equals 0. Then sometimes we say, okay, go to valve DD, although we have already opened the valve DD. So for example, oops, where is it? So here we are on valve DD at the minute 19, but we had already opened the valve DD at minute 28. So we're just randomly back on the node DD, and it doesn't make sense. There is no goal for that. The goal is always you want to go from where you are currently to one of the valve that isn't opened yet. That's it. That's the only thing you want to do. So if you're on this valve BB, you open it, you want to go to any of the other valves that haven't been opened yet. And that means the more valves you open, the less choices you have. So instead of having something that's a problem space that is exponential, each time you make a move you have like always the same number of moves available. Here we are like reducing the number of options as we progress in the problem. And instead of just going 1 minute at a time, we can say, okay, we are here, next time we want to go to I don't know, want to go to I don't know. We want to go to I, for example, from D we want to go to I. Then the best option is to go to A and then to I. So basically from D to I it takes 2 minutes, and you go from A. Wait, that's the idea. That I don't know if I was clear, but we need to change this graph. That's just a simple graph into a graph of only useful information. So what I'm thinking, so we need to create something to help us. We need to create like some kind of, for each node, we need to create the shortest path to all of the other nodes. That's gonna be a bit complex, but we can make that. So so here in the parsing, I think that's what we're going to do here in the parsing. Const object equal that, and here we return the object. So here we are going to improve our parsing, and we're going to add some useful information. So I think we're going to use a BFS starting on each node until we visited all nodes, and then we're going to have a good map to move around. So here BFS graph root, and let's just start again. Const q equal an array, const explored equal new set. You say explored dot root equal explore dot add root. So here our node should be it's root dot node. And here you enqueue q dot push root. Right? Yeah, okay. While q dot length is above 0, then const current equal q dot shift. You take the first element of the queue. If current, no, we don't care about the goal. We don't want to return a goal. Here we just care about exploring the full graph. So we need to say for each node what is the number, how many steps it takes to go to another node. BFS here. Yeah, so we're gonna figure this out here for all edges. So here you have a current node, you need to go what's the graph? We need to display the graph again here. Here we're just gonna do, oh, so this is the graph. So actually let's I don't know what I'm doing here. Process that exit 1, and here con log object. We're gonna solve this. So this is our graph. So here we're gonna do for of node of array. We're gonna do a BFS of the graph. So here instead of object, this is gonna be called graph, and this is our current node. And here we can just exit for now because we don't want to go too crazy. Here okay, so we have our graph, we have our root, we have this. Now we go to each neighbors. So for of node, let's call that node of here this is graph of current node, no, current dot valve. Oh my god, current dot valve. So for each valve, neighbor of current valve dot other valves. For each of these other valves, we check if it has been explored yet, if explored.has valve dot just valve, because this is a string valve. If it has not been labeled, then explored.add valve, and I need to say here like the parent, and q.enqueue q.push graph of valve. So this is not node, this is valve here. Let's see. In the array, yes, we have this. So now we need to store the path. We need to store the path, and how we do that. We don't need the path, actually, we don't care about the path, we just care about how many steps do we do to get to a specific node. So here we are on root. So here we say root.path. This is an empty object. And here we are exploring a path. How do we know how many steps it takes to go to this one? And here we need to do root.valve. It's 0. Yeah, we don't care actually about that. So we need to take the path to go to the previous node plus 1. So it's something like root.path of to go to the valve. It's equal to of something plus 1. And this something is to go to the current.valve. And here this can be empty, so we start at 0. Let's see what happens with that. Okay, it happens nothing. We need to log the graph again and see what happens. Okay, look at that. This is beautiful. We know that for DD, II, and BB, we just take 1 step to go there. And then for CC, for these, you take 2 steps. And for these, you take 3, 4, and 5, finally, to go to HH. Oh, this is good. Good stuff here. So here, basically, we do the BFS for each node on the graph. And then here we're gonna log the graph, and we're gonna process that exits, that we just log the graph, and that's all. And now for each node you can see that you have the path to all of the nodes. So for example, if you take HH, it should be 5 to go to A. HH, it is 5 to go to A. Yes, so we have something great. Yeah, we have something that's going to be helping us trimming down the complexity of this thing. So now we have this. Now we have to think about how we change this algorithm so that we have less options. So this doesn't change, meaning when you stay on the same node and open the valve, it's always just 1 more minute, and it's, yeah, doesn't change. Now moving to another valve that can be opened, and this thing is the change that we are making. So here we don't go to all of the neighbor, we need to go to all of the valve that can be opened. So basically we need to const option. What are these valves? We need to do object.keys of the graph. That gives us like an array of all the options. And here we filter valve, so that valve dot flow is above 0, and what are the current valve? Current.open valves of valve.valve. Yeah, maybe I should put another variable here. Getting too confusing. If this valve is open, so we haven't recorded something here, we haven't said it is open, so it is still closed. This is an option. So now we can take that as an option for each valve. Actually here we can do it like that, because yeah. And now the time is not that -1. The time is how much time does it take to go from current.node? What is current? What is, oh, current node? This is this thing. Current.nodes.path to go to the node valve. Const steps, we put it here, minus steps, and here you do steps times add flow. So that's it. Now we just move towards the closest unopened valve, and you can open it or move to another. Oh wait. We need to change our algorithms. Because basically here what we need to say, we need to move to the closest valve and open it. Here we are opening the valve because we are moving at random on the map, and if you have an open valve that can be open, you try to open it. But here we're actually gonna remove that. We're gonna remove that. We move because we move to another valve that can be opened. So we say move and open the valve. So this is this +1 because you move and you open the valve. And basically I had copy pasted that. You need here, you need to do that. Open valves, current open valves, and this is not current node here. This is the valve that you go to, and it's not current time -1, it's current times minus steps. I think it is time to run our algorithm and see how close or how bad, how far we are from the truth. So current time is below or equal 0, then we push current. Okay, we have just one thing. Doesn't look correct. That's fine, you know, we are going step by step. So this we can remove because we don't care about that anymore. We have our end condition and then we just here move to another valve that can be opened. We open it and we go on. Maybe you opened all the valve. So let's see. Here we can say if option.length is equal to 0. In that case, here endings.push current, but that's not true because this is not exactly current that we need to make the simulation go to the end. Okay, here to do make the simulation go to the end. Is there like a place we need to be at the end? Yeah, no, okay, so here what I'm seeing is that here most likely we have opened all the valve here, and here we're just waiting. Yeah, we're not even moving. So basically this is this scenario. We have opened all the valves. Now we need to just wait until the end. So let's console log no, let's actually do that. We're gonna make the simulation go to the end. So we're still on the same node. We're not moving. Current dot node. We're not moving. Time is gonna be equal to 0, and here flow is gonna be equal to current dot flow plus times add flow. Yep. And the open valves is gonna stay the same. Current dot open valves. Let's see that again. Oh, that is not working. Console log. Here we display current here. Let's just display something. Okay, this is not working at all. Not working at all. So let's debug that. We know this. Wait, current time above or equal to 0. That's a stupid thing to do. Below or equal to 0. But I think this is never gonna happen. Okay, we are not moving. We are on. Okay, so we need here to display the option. Console log options. The option is an empty array. That doesn't look good. We're gonna fix that. Log option keys of graph. That's basically. Oh, I think I was not expecting that. I think I wanted to do option values of graph. Oh yeah, that's the problem that was happening. So I was just getting the keys or when I wanted to access the thing from the value. That was the problem. So here we can remove this. I think we reached the simulation to the end. So we have 620 ways we can do all these things moving around. So basically what we need to do is we need to just do math.max ending.map x.flow. And if we do that, we get 3,820, which is not correct. So Let's just display console log options. Oh, I know. Look at that here. I used, one more time, I used time instead of current.time. Ooh. Let's just actually Control Z. We keep that here, the max, and here we do current.time. Wow, that was, oh my god. This is correct. This was the small bug. Oh, sometimes it feels good to just find the bug and solve it. Let's see, now we're gonna just rush and see, can this work with the full input? Oh, this is taking a lot of time again. So, we have made a lot of optimizations, which is good, but this is not enough. Although there are a lot of valves with flow 0. I don't understand why it's taking so long. The branching factor shouldn't be. Oh, you know what? I know what we should do. We should check how much time is it taking to do the parsing here. So here on console log parsed. Okay, so it was really fast to do this, all this BFS here at the beginning. So it's hard to know what's happening. I know object.values is really bad. Object.values plus a filter. So maybe that I need to do something a bit better here. Doing something great though. Yeah, this is taking far too much time. So back to finding the performance issue culprit. Let's see. Have we reached already an end somewhere? We're not reaching the end. Let's display the current here. Log current. Wait, there are minus numbers here. I've seen some minus. Here, -2. Okay, so that's interesting. So we went below 0. That is not good at all. Yeah, you see the time is minus something. So it means we were not able to... Okay. But here, if I do current.time, below or equals 0, ending.push, and continue. So it should be... Yeah, I mean, there's definitely an error, but it should never happen, right? Yeah, so here, yeah, okay, it still takes a lot of time to go through each of the options. Yeah, here we are 4 nodes. One, two, three, four, 5. Okay, this is just gonna take forever. So we've done a smart optimization that is not good enough. So one thing I would love to do is to fix this, where here we have log current time. We have some minus here, that's not good at all. So here we need to check if the option, we need to check if this is below 0. In that case, we need to just say, okay, we can't move to the next node, we just need to stop. That's it. So here, and else we do this. So here, what do? We do something. This should never happen actually. Here we need to throw new error. Should not happen. Because here this is our end condition. We have two places for our end condition. One is here when there is no more, we have visited all the nodes that we can visit, and here we are at the end of our time budget. So in that case here we need to do something similar to that. The current node time is 0 and its current flow plus current times add flow. Yeah, that's it. That's it. And if this is exactly equal to 0, what do we do? That means we have no more actions left, so it's that, like that. Okay, let's try that again. Yeah, we have no minus here, but still, let's see. I'm gonna let it run for like 30 seconds, just see what happens. That's interesting. We got actually maximum call size exceeded for math.max. So maybe in endings here, we don't need all of the information. Actually, we just need the flow, right? We don't need to know where we ended, what valves are opened. We just need the final flow. So let's try that. Here, I'm just replacing everything by this endings.push. Actually, we can do something even better because this is the max const best max flow equals 0 here, and here we say if const flow or ending equal this, if ending is above max flow, then max flow equal ending. That way we don't need to store a huge array, and we just have one number, and we can just display here max flow. Let's try that again. I'm gonna actually time it now, and we see how long it takes to find the solution. Assignment to constant variable, that's the thing I'm always doing. You've seen it so many times in these videos. Thankfully, it's quick to fix. I've run time. I'm gonna pause and see, we are gonna see the results. Okay, so it took 60 seconds and we have a value here. I think it's time to just input it here. Oh yes! Yes, that feels good. This is our gold star. I'm gonna read the print statement on part 2, although I believe I won't do it, but I'm gonna still explain a bit what my thoughts on that. So I think I think we're not gonna make it work with our current solution, but I think it's worth trying. So we're gonna try that. So we take the small input, because we know this goes fast and it's could be a good win to just actually see the solution work with the small input. And now we take our long code from part 1 and we put it here on part 2, and we have here only 26 minutes if I'm not mistaken, because we have to spend 4 minutes explaining the elephant how to handle the valves. So here we're actually going to comment out part 1 because it takes 1 minute to run part 1, so we don't want this to block us on part 2. So here we have to, our state is going to be a bit different. Instead of node, we are going to say node human and node elephant. Yep, and we start both at the node AA. The flow is common for everyone. This is a state that's not just for the human or just the elephant. The valves as well are common for everyone. We still have our max flow. And here we still want to list the options, but here we want to do something a bit different. We want to go through each combination of 2 options. So that might be adding far too many states for our program to run the full input, but as I was saying, let's code this dummy implementation for the small input already. So we're gonna do a for loop, a double for loop. So this is gonna be I between I and options. And this is going to be another for loop. We see j between j and options.length. And here I'm going to say if I is equal to j, then you continue. We want to skip this thing. Actually, we can say if this is different, then we can do more stuff. That's a bit better. So if we have to, oh my god, no, that's not going to be possible. No. My solution is not gonna work because it's gonna take a different time from the elephant and the human to move from one node to the other. And so, yeah, oh, that's tricky. So tricky. So actually we don't really care. So either both are done moving, that's gonna be complex. Human moves remaining, elephant moves remaining. That's just not gonna work. Yeah, I think I'm gonna stop here because the problem is that both the human and the elephants are moving at a position that is not the same that doesn't take the same time. So I need to find a way to stop. Yeah, maybe that's another video later in the future, but I think part 2 is gonna stay empty for today. That happens, and the most important is to have fun and to learn a few things. And today we've learned this thing that was really useful. We've learned how to simplify a graph into a more useful graph that enabled us to solve the problem in a okay amount of time. Not perfect, but hey, we've done it. This is all for today. Thank you very much for the support in this series. See you tomorrow for another one. Bye bye.